How's it going, everyone? Mr. D here. In this video, we're going to be discussing special cases of factor patterns for factoring quadratics. So, if you are comfortable with factoring problems that we just talked about in Target 3, you will have no issues with these Target 4. This is more of like an enrichment that if you're a fan of shortcuts, you can kind of pick up on some shortcuts here. So, the big concept that you always want to be on the lookout for anytime you're factoring with these special patterns is you want to keep an eye out for the first and the last term and whether or not those things are perfect squares. And perfect squares means we could take the square root and get a clean, pretty number. So, do I know the square root of x squared? Yeah, I do. It's just plain old x. So the square root of x squared, if I were to square root that, I'd get a plain old x. The square root of 9, do I know the square root of 9? Yeah, that's just 3. So as soon as I notice that I've been given the green light to maybe proceed, based on the fact that I'm starting and ending with perfect squares, the next thing I'm going to look at is the middle term. If the middle term is twice as big as the square root of our last term, so if the b value is twice as big as the square root of the c value, the special pattern that we get to employ is this, x plus 3 quantity squared. So this is what x squared plus 6x plus 9 would factor down into. Now, if we didn't know that special pattern, right, and we were just kind of factoring it normally, and we're trying to figure out, okay, I know it starts off with an x and an x. Now I need two numbers that would multiply to be a 9, but add up to be a 6. Well, the only opportunity to do that would be 3 and 3. So we can still get that result by factoring it out the quote-unquote long way, but now we have a few shortcuts in our arsenal. All right. So if we were to distribute this out, right, x times x is x squared, x times 3, 3 times x. That's two different occurrences of 3x. Add those together to get a 6x. 3 times 3 is 9. Next one, x squared minus 2x plus 1. All right, so again, first and last term, those are both perfect squares. Okay, so ideally I want to start off with that, if I can. Now the real check is this middle term, this negative 2. Is negative 2 twice as big as that number? Is 2 twice as big as 1? Well, if I make that 1 a negative, then yeah, it would be. Negative 2 is twice as big as negative 1. So that's our factored form. Now things will change a little bit. Oh, maybe I'm jumping the gun. When we have a coefficient, so this example, things might be a little different. Let's see one more here. X squared plus 10x plus 25. Again, we could factor this out the normal way, or we can kind of use our special patterns. I start and end with a perfect square. I start and end with a perfect square, so mentally I'm thinking, okay, we have an x and a 5. Hopefully this will check out. And as long as this middle term is twice as big as that 5, then we're good to go. And 10 is in fact twice as big as 5, so we can write that out. All right. How many more we got? All right, let me do this problem here, and then we'll get into numbers 4 and 6. All right, so for 4x squared minus 12x plus 9, this one's going to be slightly different, but it's still going to follow the same logic. So we're going to look at the first and last term, right? Are those both perfect squares? Do I know the square root of 4x squared? Well, the square root of 4 is 2. The square root of x squared is x. Do I know the square root of 9? Yeah, that's just 3. So normally when we check this middle term, right, we've been saying we want this middle term to be twice as big as that guy. Well, 12 is clearly not twice as big as 3. So we're running into issues here. Instead, what we need to do is figure out, is 12 twice as big as the product of both of these terms? On the previous examples, there was no coefficient on the x value right here. It was just a 1, so I didn't really need to factor that in, right? But now I've got a coefficient of 2. So I need to figure out what is the product of 2x and 3, and then is 12x in fact twice as big as that? Well, the product of 2x and 3 is 6x, and yeah, 12x is twice as big. Since it's negative, I need to make sure that that 3 is negative. And then we're good to go. We are good to go. The general format for these, I'll write this down here in red in case you want to have these written down, is if you see something that can factor out into the form of a plus b quantity squared. This would be written in distributed form as a squared plus 2ab plus b squared. So the a value is the square root of that first term. The b value is the square root of that last term. It's going to look the exact same thing if it was a minus with just one slight difference. And that is the middle term, the 2ab value, is going to have a minus sign in front of it. That's the only difference. All right, let's get into the last special pattern here. X squared minus 16. This is what is called the difference of two squares. Difference meaning subtraction. 2 meaning there's two terms. Squares meaning I can take the square root of each piece. So if I can take the square root of the first term and square root of the last term, sirens go off in my head. Maybe I can use a special pattern. You'll notice, though, there is no middle term to check with, right? There is no central term here. So what gives? Well, that middle term, when we have our factors, will essentially kind of be canceled out. And I'll show you what I mean. So if I have x squared minus 16, I know the square root of x squared is x, and I know the square root of 16 is 4. When I factor this out, I'm going to factor into what's called conjugate pairs. Now, just for fun, we're going to distribute this thing back out. When I distribute, it's going to get to x squared minus 16. So we already know the answer, but x surprised when we get there. When we distribute this out, I'd have x times x, that's x squared. I'd have x times negative 4, that's a negative 4x. Then I'd have 4 times x, that's a positive 4x. And then 4 times negative 4, negative 16. These two guys right here, these two terms, those are going to knock each other out, leaving me x squared minus 16. So anytime we factor things down into conjugate pairs, those two middle terms, they won't combine to create a new term there. They'll actually cancel each other out. They'll nullify one another. This pattern only works if you have two terms separated by a minus sign. If this was a plus sign in between, you cannot do this pattern. Again, if this was a plus sign, you cannot do this pattern. That is why it's called the difference of two squares. All right, one last one, and then we is done. Where did my thing go? Holy smokes. There we go. All right, 9x squared minus 16. Ooh, numbers are kind of big on this. Is there GCF? No, there's not. No common factors between 9 and 16, other than 1, but that doesn't count. Well, I'm noticing we've only got two terms separated by a minus sign. They're both perfect squares. So the square root of 9x squared is a 3x. The square root of a 16 is 4. And if these have to be conjugate pairs, one gets a plus, one gets a minus. It doesn't matter which one goes where. That's it. That's all, folks. You know the drill. If you have any questions, please let me know. And always, good luck, have fun, be safe, roll tide.